Good morning, everybody. Thank you for attending the webinar, Economics of Energy Efficiency and Fuel Switching for Commercial Scale Buildings. We're very happy to have you here. My name is Josh Valentine. I'm a communications manager with the Clean Coalition. And a few things to go over before the webinar begins. If you see in your control panel, you will have a functionality to ask a question and receive an answer potentially at the end of the webinar. Depending on your operating system, this could look a little different from computer to computer, but feel free to ask a question and we'll try to answer it at the end of the webinar. The webinar recording and slides will be emailed and uploaded to our website within the next 2 days. And it'll also be on our YouTube channel. Also, please, if you're using social media, use the hashtag PAEC chat to join the conversation on Twitter. So today, we have speakers from DNVGL, and we're really happy to have them here speaking with us. Betty Seto, she is the head of Department of Sustainable Buildings and Communities, and Blake Herrschaft, senior engineer for Sustainable Buildings and Communities, both at DNVGL. So we're going to get right to it, and we're going to hand it off to Betty right now to begin the webinar.
Okay, great. Thank you so much, Josh. All right, so I need to share my screen. Okay, is that coming through?
It is indeed. Thank you.
Okay, wonderful. So yeah, so we're very happy to be here today. The economic analysis that we'll be presenting was completed as part of the Clean Coalition's Peninsula Advanced Energy Community initiative. The project has numerous project partners working together to achieve the vision of an advanced energy community. Okay, so in terms of project funding, the PAEC project is funded by the California Energy Commission's Electric Program Investment Charge Program through the EPIC Challenge for Advanced Energy Communities. So the PAEC region, for those of you who aren't familiar with the project, it is defined as all of San Mateo County, including the city of Palo Alto, our honorary jurisdiction. But there's also a core PAEC region that's the southern part of San Mateo County, encompassing the cities of Redwood City, Atherton, Menlo Park, and East Palo Alto, as well as the unincorporated parts of the county in the southern part. But I would like to emphasize that while the project analysis that we'll be presenting and describing is focused on this specific core part of the PAEC region, the methodologies and the key findings are widely applicable to any region in California and beyond. So you may be asking yourselves, what is an advanced energy community? So the PAEC initiative includes these key components of a AEC, Advanced Energy Community, which includes abundant solar electricity, energy storage, and other distributed energy resources, as well as low or zero net energy buildings, solar emergency microgrids, and also a EV charging master plan. You know, how do you bring that together to reduce emissions, to you know, improve quality of life and support you know, active and healthy communities? There are a number of PAEC project goals. So first of all, of course, accelerating the deployment of the AEC, you know, key components within the region, but also reducing the cost and the uncertainty in the permitting of you know, DER, storage, microgrids, and interconnecting these advanced energy technologies onto the grid. And of course, reducing energy usage and reducing energy demand. The project does have a goal of reducing 25 megawatts of peak energy, and then also reducing natural gas. And minimizing the need for expensive and costly utility upgrades for the system. And then finally, as I mentioned, you know, creating project deliverables and analysis and research that's scalable and scalable to other communities across the country, and that can be also replicable as well. So reducing natural gas is one component and one specific part of the project, and I wanted to spend a little bit more time on why that is and why local governments in particular are so interested in moving away from natural gas. But this pie chart shows the greenhouse gas footprint for San Mateo County, the entire county, for 2014. And you can see that together, you know, the residential and non-residential portion of the pie, you know, that's the buildings. It comprises about 34% of the total footprint. And of that, you know, natural gas is right now about 18% of the total footprint. But as more and more local governments are moving towards 100% renewable energy, in San Mateo County, they now have Peninsula Clean Energy with higher renewable energy products for the community. The natural gas wedge of the pie is just going to increase. And so you can see that, you know, in my mind, the natural gas wedge and the transportation wedge remain what I call the final frontier for emissions reductions. So, you know, Blake will talk more about this as well, but I wanted to just tee that up with a little bit of specific data from the San Mateo County region. So I think with that, I'll turn it over to Blake to walk through the technical analysis and the key findings.
All right, hi everyone. Thanks for joining our webinar. Let me know if you can't hear me or see my screen. So I'll go through the technical analysis we performed under this grant. First, wanted to go through the energy use breakdown of a typical commercial building in San Mateo County. This is basically an average of all commercial building types. This is specific to San Mateo County. It changes a little based on climate, where space heating and cooling loads will change. What you'll see is the biggest is that electricity accounts for 64%, so 2/3 of the load. And then the biggest loads on an annual basis are in a typical existing building are interior lighting, cooling, ventilation, refrigerators. And then on the natural gas side, we're looking at heating, water heating, and cooking as our big users. So that's the biggest slice of the pie we can hit when we walk through and look into how to reduce energy use at each of these prototypical buildings. Betty mentioned that as we go to 100% renewable electricity grid, the two remaining portions of carbon emissions are transportation and natural gas. So electrification is becoming more of a topic. We've looked into this a little bit as part of this project through some of our energy efficiency measures. I just wanted to walk you through a couple of those issues and scenarios. Some things to consider here. Once we get to high renewable penetration, as we've discussed, natural gas is going to be the biggest building-related emitter. This is already true in some cities, such as Palo Alto, that are already at 100% renewable electricity. Another thing to note, 25% of all US homes in the United States are all electric. This presentation is mostly about commercial, but you would see this scale equivalently. So the fact that in a lot of cases, when we look at existing buildings, we think that electrifying is this hard new concept, but the fact is that it's been going on for 50 plus years, and that a lot of our existing building stock already does use electricity for thermal loads. And then in a very cold climate, just something to compare to, and since DNVGL is a Norwegian company, we always look to Norway for some solutions. They've been all electric, 100% renewable for a number of years, and sometimes the sun doesn't even come out all day. So that's a useful case to look at of a cold climate that's succeeding in that way. These are just some recent articles that show the hazards of natural gas that had come along over the past 5 years in my time. So it can be a dangerous thing, as we've seen in some pipeline safety issues and home safety issues over the years. The next question is, I had always thought of biogas as a really big solution here, and a reason that you would stick with natural gas as a thermal solution. And I'm a mechanical engineer, not an electrical engineer, so there's a benefit to me if we continue to use molecules for energy instead of electrons. So what you're seeing here is the U.S. Natural gas use in 2013 with the breakdown of residential, commercial, industrial, and power plants. And what I was really curious about was if we were able to collect all the biogas in the US, what would that look like? So the National Renewable Energy Lab did a study of the biogas potential of the United States. That's collecting all landfill gas, all wastewater biogas available, as well as all products related to compost and cow manure and stuff like that. And I was wondering, is this 25%, 50%, where can this get us? And what the NREL study shows is that this is the biogas potential if we collect everything in the US. As you can see, that's not really enough to get us there. And where we really need this gas is probably going to be in the industrial sector, where we have to do intense things like melt metal that are really hard to do with electricity, as well as the vehicle sector where we might look for planes, trucks, trains, or cars to run on natural gas. I think that if there's a reasonable solution in residential commercial to avoid it, then we can't stand to spend our precious biogas on those solutions. This was released in November 2017, so just a couple months ago, by Southern California Edison. It's their clean power and electrification pathway to meet the state's environmental goals. And what we're seeing here is just that more utilities are starting to jump on board of electrification as maybe the only way to get to some of our aggressive greenhouse gas goals. So two things we looked at during this study was how we can do heating, ventilation, and air conditioning with natural gas. We looked at variable refrigerant flow systems as well as packaged heat pump systems, which essentially run the air conditioning system in reverse so that you can create thermal energy with electricity that's highly efficient. The efficiency is usually 300, 330%. On the domestic hot water side, heat pump hot water heaters are getting a lot more popular since they've come into the US in 2009. There's a few companies making them now, and again, they give us an opportunity to go from 60 to 80% efficient on traditional gas storage hot water heaters to 300 plus efficiency using a heat pump hot water heater. Now we'll just go into the energy efficiency analysis that we performed as the part of this study. The first thing we did was go through our building types and select the appropriate buildings to target zero net energy that are the most common in this region. And these are also some of the most common building types in cities around the United States. Then we looked at the baseline building vintage based on that region. Vintage is really important for reasons I'll get into later. It's all about right timing so that the cost of your equipment, so you're only dealing with the incremental cost to buy high efficiency versus code minimum efficiency when you do a replacement instead of paying for the whole system and trying to pay back for that with the energy savings. And then we looked at baseline and proposed efficiencies based on those vintages and based on what the best available in the market is. The 5 prototypical buildings we went with were an office. We looked through a variety of data, including department websites, LoopNet, which is essentially the commercial version of Zillow, as well as CBEX and REX, which are the commercial building energy consumption survey and the residential end-use consumption survey in California, which kind of give an average range of certain building sizes. So we studied an office building of 10,000 square feet that's 2 stories, the energy model kind of version of which is shown there. A multifamily building that includes 5 units, a 5,000 foot retail with storefront, a school which is 8,000 square feet, 1 story and 4 classrooms. That might be the one that tends to start to be different among different regions in the US. In colder and hotter climates, you tend to see much bigger schools. In California, you see a lot of clustered schools with exterior hallways, which means you don't have to condition the hallways. And then for municipal buildings, the assumption at the beginning was that we might go with a municipal office of some sort, but the municipal building that we see the most common is actually fire stations, and that's because they have to be peppered throughout a city so that they can respond to fires quickly. So whereas each city has one city hall, they might have 7 to 30 fire stations. So we wanted to study fire stations because they're on almost every capital improvement plan cycle because there's so many of them. So when we went through this economic analysis, we looked at the capital costs of the equipment, the incentives that are available locally for that equipment, O&M, operation and maintenance costs with the baseline equipment as well as future replacement equipment, financing options, and energy cost savings from our energy simulation results, which I'll walk through all of that now. For each energy efficiency measure, wanted to go through kind of the costs associated with those. So, and you see so let's start with the baseline cost is 0 until we go into each piece based on how old the building is. LEDs, depending on the building size, are costing $7,000 to $27,000. We also looked at a building management system, which is basically HVAC controls, which aren't on a lot of these 1995 buildings, or they're not as smart as they would be today. Reducing phantom loads. Phantom loads is a name for the loads that happen from all your electricity sockets when you're not in the building. The most traditional example of a really high phantom load are those old hi-fi stereo systems, which tend to draw a lot of energy by just being plugged in. Modems that are plugged in but aren't being used are another example of phantom loads. As well as going low E, adding tinting. For insulation, we looked at blow-in insulation in most cases because in an existing building, that's the least expensive option and gives you the most bang for your buck. For air conditioning, higher air conditioning systems today, especially for these building sizes, are much higher efficient than they were in 1995. For heating, we looked at converting to a heat pump in order to triple or quadruple our efficiency. And then for hot water, we went through that before. We looked at solar hot water as well as heat pump hot water systems. For our baseline equipment assumptions, I'll go through these quick because I know these tables can put people to sleep, so I apologize for that. For everything, we looked at basically 22-year-old equipment, except for interior lights. In a lot of cases, that would be incandescents, but at this point, they would have all been reduced by fluorescent lights. So that's what we used for interior lighting, 1.5 watts per square foot for phantom loads, and then the rest of this will be available to you when I send it through. And you can see kind of here the existing and here the proposed measures. Our calculation methodology, this is really important. Energy modeling software is really good at certain things, and for some things it tends to not be the right tool for the job. So we used a variety of 8760 hand calcs. There's 8,760 hours in a year. We use those for interior lighting, exterior lighting, and hot water calculations because that's it gives you a lot more control, especially on the hot water side. Energy simulation software used in this case, IES's virtual environment. It models hot water, but it's a little bit better to do outside of the software. Energy simulation software is really important for looking at the effectiveness of everything that has to do with weather. That's insulation, windows, air conditioning, heating, and the improved performance when you add a building management system. Let's walk through some of the results. And before I go through those, I kind of want to orient you because the next 5 slides will use the same kind of pattern. What we have here for the office is the baseline energy usage of an average California office of this vintage is 59 kilobTUs per square foot per year. The proposed energy usage you'll see to the right of 22 kBTU, that's about a 60% reduction in energy use through using these measures, 63 I've shown there, with a 5-year payback. On the right side of the screen here, we're showing which measures have a short payback, a longer payback, and in some cases, no payback. In this particular instance for the office, where there's very little hot water usage, the hot water heater did not show a payback. That's in part due to the ultra low cost of fracked natural gas as compared to a much higher cost of electricity, especially within California, where we pay fairly high electricity rates. And then here at the bottom left, what you'll see in the office is the top total energy savings by energy efficiency measures. So that's not the fastest payback. That's just what gives you, what kind of helps reduce this 59 to the 22. As you can see here in the office, you're getting a lot of savings from heating, windows, lighting replacement in every case, which is also a very short payback, and insulation. I'm going to do a deeper dive into the office in particular, so we'll go through that line by line when we get there. And now I'll walk you through how this sort of changes when we go through each of the 5 proposed building types. For multifamily, you see kind of similar baseline and proposed energy use. I want to bring your attention to the fact that they just use a lot more hot water because people are taking showers and cooking and doing dishwashing in these areas. So hot water becomes a really important measure. Heating is also big savings, especially because these tend to be occupied at night where a lot more heat is used, even though it's been really hot during the day. Where I'm sitting in San Diego, I had the heater on at night. It just uses a lot more heating. Windows become a big energy saver, as well as LEDs. And then your top payback, air conditioning has a really fast payback, even though it's not necessarily the highest total savings. We jump into retail, very similar baseline and proposed energy use in terms of energy used per square foot per year. Heating, LEDs, and insulation tend to be the big winners here. When we jump into our school, again, heating, LEDs, and insulation turned into a lot of energy savings. This is really, energy savings is really going to be based on the existing school type. A lot of schools of this vintage, 1995, relied on electric lighting and day lighting. The school I grew up going to was about 100 years old, so it had really good daylighting, and we didn't use the lighting as much, so lighting isn't as big of an energy savings. But in this particular vintage, what you'll tend to see is that the classrooms don't necessarily work very well without lights, so switching to LEDs really does save a lot of energy. Now jumping to our fire station. The big energy saves here, again, you see your LEDs, insulation, and heating. Hot water didn't have a real payback here. They do use a lot of hot water in a fire station because every shift, most firefighters tend to take showers because they're either working out or they went to a fire. But here, because of the high cost of electricity compared to natural gas, the payback wasn't essentially good. However, when we show bundling, here's a way to save carbon emissions of measures that might not have the best payback, but still save a ton of carbon, which in the end is the goal. Now I want to look at our savings comparison by building type. This is kind of a table of the energy use intensity that you saw previously, as well as the average payback in years for each case. You'll notice the school has the longest payback, as well as retail, with shorter paybacks being seen in the fire station, the office, and the multifamily setting. One reason for schools having a kind of longer payback is because they have, especially since we studied classrooms, they tend to have less occupied days per year. So the less hours you use something per year, the longer your payback will tend to be. Whereas you see the fastest payback is on the fire station. Fire stations are occupied 24/7. And this is just kind of a note that if you work for a municipality or any place with a large building portfolio, if you really want to get a lot of bang for your buck for your first few deep energy retrofits, it's really important to look at places that are open 24/7. They'll have lights throughout the facility that are on 24/7. Heating, ventilation, air conditioning systems are on 24/7 without any kind of setback. Fire stations, police stations are really good examples of those. Wanted to kind of jump into what bundling means here, and I know it's a very tired example, but I think the right one in terms of picking the low-hanging fruit. We've often said pick the low-hanging fruit first. However, if you go through and pick the low-hanging fruit first, you might not have the best payback when you go to implement deeper measures. And I think what we want to push here is that if you use holistic approach to building energy efficiency and do a deep energy retrofit, it can be better than doing piece by piece. I've used an avocado tree as opposed to an apple tree because that's the only type that I've had in my backyard in the past. So let's go through a quick example of what picking an avocado tree might look like, and then compare it to what we're doing. So if you do just the bottom half of the tree, you might get 100 avocados and do it in an hour because you don't need a long picker or a ladder. So you're making about $200 an hour. But then when you go back to pick the top half of the tree, and I have left avocados on the top half of the tree, it's going to take you a lot more time. So if you do both of those together, you'll be able to pick the whole tree and do it for a price that kind of makes picking the top of the tree reasonable. And what we're pushing here is kind of go after all the energy savings at once if you can, and you leverage the more cost-effective picking of the low-hanging fruit to pay for kind of picking the top of the tree. In our case for this building, the kind of stuff that pays back really fast is lights, pumps and motors, and phantom loads. Whereas the things that may pay back a little slower is fuel switching, adding a building management system, and especially replacing windows and sometimes insulation, depending on what kind of insulation you go with. What we want to do is go for whole building energy efficiency and bring down our energy use as far as possible. So leverage the low-hanging fruit to pay for the top of the tree to get yourself some whole building energy efficiency. Let's dive deeper and see how that looks on this table when we look. This is specifically for the office building. First, I'm going to go through, actually, I want to go through the capital cost of the measures first. Sorry that these are in reverse. Let's go through the capital cost of each measure so you have an idea of what's here. And I really want to jump into one in particular. So when we look through, one of our higher cost items is actually LEDs. But has just such a high annual energy savings. So you'll see the highest annual energy savings is connected to LEDs. Even though it's the second highest in cost, it still has a pretty rapid payback. There are also pretty high incentives available for LEDs. That's where our highest incentives are. That's why you're seeing a lot of people switch out. I call 2015 the year of the LEDs, when LEDs became came to scale in terms of something that we can replace throughout all of our buildings. And I would guess that by 2025, we'll have replaced most of our fluorescent lighting with LEDs, which is really a godsend because even though it saves a lot of energy, no one really likes fluorescent lighting. So I'm glad we're moving in that direction. Just better color temperature, no buzz, able to really dial in that color temperature and dial in dimming because LEDs provide innate dimming capability. I'm going to jump into windows. You'll see that the window replacement on the office was $70,000, which accounts for almost 2/3 of the total cost of all energy efficiency measures. Windows are really hard to justify in terms of replacing just for energy savings. If you want to do a window upgrade through a deep energy retrofit, and I think the best example of this is the Empire State Building, which went through a deep energy retrofit about a decade ago, and they did replace all their windows, and they ended up with really high quality windows, which provide really good sound protection, and also provide better lighting for the space, provide a more comfortable space, but they can be a really expensive measure, so it's important to bundle them with others. And the next one I wanted to really jump a little deeper on was how low these AC and heating costs are in terms of capital cost. You'll see 2,000 for air conditioning and 2,000 for heating, which is much less than the total capital cost that the system would cost for this particular office case. The reason for this is we're using incremental cost. If the building's built in 1995 and it still has its existing HVAC system in, then it's certainly ready for that system to be replaced. It's probably breaking a lot and needing a lot of maintenance anyway. So when you assume that the system's going to be replaced anyway, a cost that was maybe $30,000 to replace would probably only be something like $35,000, $36,000 to get a much more efficient system. And oftentimes for the type of heating, for the type of HVAC system that you see on a lot of these office buildings is a rooftop package system, which the typical office building currently is a rooftop packaged unit, which is an air conditioning system with gas built in. When you replace that, you want to replace it in kind so that you don't have to replace all the ductwork throughout, and you can keep the cost down. Typically, if you go to a contractor and ask them to replace their unit, they're going to replace it with the same kind of unit just to today's minimum efficiency standards. That means they're going to automatically replace a gas-fired unit with another gas-fired unit. For an extra, what we have here is $2,000 to be conservative, but it's probably closer to $400 per unit. You can switch that to a heat pump, which basically adds a reversing valve and uses the air conditioner to run backward and just vastly increases efficiency. But you have to know that's what you want when you order it, otherwise they're not going to help you. I think for building owners, the lesson here is to just be really prepared for when a replacement's coming so that you get what you actually want and don't miss a really good opportunity to replace with high efficiency equipment at low cost, because you only get that chance every 20 years. I think for municipalities, the lesson here is to either get education out there to your building owners or create some kind of hotline so that when a system breaks and they have to replace it the next day so that their tenants or if it's owner occupied themselves can really still occupy the building, you want to have a way for them to know what they want in a timely manner, because usually these replacements happen really fast when they break down. Now I'm going to jump into the energy savings and the IRR for each of these measures. I think what you're going to see here is your quickest payback, and which means your highest return on investment, and we're talking about late 2017 Bitcoin returns, are 38% return here, 2.5-year payback on LEDs. If you haven't replaced your lighting system yet and your building's occupied most of the year, it's time to do it. You'll get better lighting, you'll get new lights, and they pay for themselves. Looking at phantom loads pays back really fast because it's just about behavior change. Another measure that's really paying back here, especially because we're using blow-in insulation, is insulation. And then our heating system, because the cost was so low, the payback's really fast in this particular case. The total savings, and then what I guess I want to really note here is that windows have a really long payback. Typically 11.8 years is longer than the threshold people would be able to handle for most windows, but once we bundle them all together, we can afford all the ECMs and have a bundled 5.5-year payback, which is pretty fast and really something that pays for itself, and you end up with all this new equipment as long as you do it at the right time. And the savings over the system life is $320,000, which is a substantial amount of savings that can be spent on other parts of your building portfolio. This is a summary of all the paybacks for each different type, for each measure, for each building type. If you look at the bottom here, we have a legend that has moving from left to right: school, multifamily, retail, office, and municipal. We already went through what kind of have the quickest bundled paybacks, but our municipal building, mostly because it's occupied all year round, in this case the fire station, really has your quickest bundled payback for hitting all those energy efficiency measures. So in summary, from our analysis throughout for every building type. Reducing phantom loads, adding LED lighting were big savers. Adding rooftop heat pumps for air conditioning is also a big energy efficiency measure there. Due to the low cost of natural gas, heat pump hot water heaters end up actually costing more in most cases than traditional gas hot water heating. That's something that may change if gas prices go back up, but they've been down for quite a few years ever since we've tried to kind of increase our hydraulic fracturing and become energy independent across the United States. So that's something that we kind of have to deal with. If we want that to flip, that's more of something that will have to happen at the policy level than an individual building owner can necessarily control. Now I want to spend the rest of the presentation going specifically through the benefits to owners and property managers. First, I'm going to go through kind of the pitch that you can make to a prospective tenant. I'm using an example that's really that I'm going through right now. We're planning on moving offices. In the office I'm sitting in right now, I will not be sitting in at the end of this year. And we've all been kind of working together through that process. For the average office, we're looking at about a $2 per square foot cost in our region. And then when I went through and looked at the average kind of energy use intensity and multiplied that over to see what it costs per month, that's an extra 25 cents per month in gas and electricity costs that a typical tenant will be paying, which is a 20. Also in this case happens to be a 13% increase. It's a pretty big deal. So if we go through and do this deep energy retrofit process based on our prototypical building, there's a savings of 16 cents per square foot per month that can be realized by either the owner or the tenant, depending on what kind of lease that is. That brings the total advanced energy community office costs to $2.09 per square foot per month. Per month, and what that really means is you're to DNVGL that Blake's going to sit in, which is you can charge an extra $1,280 per month if the costs and your utility bills are inclusive to your rent, which is the case in the office I'm currently sitting in. I'm not sure if that'll be the case in the future, or if your tenants do pay their own electricity bills. You can help entice tenants by letting them know that in our particular case, we're looking at 8,000 square feet. We can reduce our energy costs by $1,000 per month, which is a pretty substantial savings that can be spent on what I'm hoping is a foosball table. We'll see. Next, I want to go through sort of a classic example at this point of a deep energy retrofit. This is the DPR Construction Zero Net Energy Office in Phoenix, Arizona. On the left, you'll see what the building originally was, and on the right is a photo of the building as it stands now. Has a lot of really sustainable features. It was originally kind of a junky, tilt-up, actually site of an adult bookstore, and is now one of the nicest construction offices in the country. It's got all kinds of, in a really hot climate. So as you can see, it looks a lot better and is a lot better to bring clients to. There's a lot of sustainable features here like solar panels. These are thermal chimneys, which uses natural ventilation. All the windows are operable. It's got a big phantom load switch that I don't have a picture of, but the last person out of the office kind of hits a giant red button and turns off all the phantom loads that aren't integral to processes to kind of get down to that deep level of energy savings. But what does that mean for DPR who bought this building? The original value of the building when they purchased it was $800,000. After they made all their upgrades, a lot of which were energy efficiency related, the property value is now valued at $1.8 million, which almost paid for the whole retrofit, just the increase in valuation. So that's a really good return on their investment, and allows them that if they want to sell this building in the future or borrow money against it, a lot more leverage. So now we've gone through kind of how property owners can make kind of bigger pitches for continual savings if they're renting out their property, and can also increase the total value of their property. And now, before we end, I'm going to go through the last benefits to owners and property managers, and kind of a list of other stuff that I didn't dive quite as deep into. Well, new equipment that basically pays for itself. That's what we saw when we saw those payback. Everybody would like a building where everything's recently replaced. And this is an opportunity to do that and have it actually pay for itself. You'll often get less complaints due to old equipment. I bet that most of us have worked in an office space where the heaters or air conditioners were constantly needing to be maintained. If you're able to electrify your space, you'll have increased safety from natural gas leaks and carbon monoxide poisoning. It's a real problem. Every home and building in California has to have carbon monoxide sensors at this point because it can be a dangerous thing, obviously. You get more marketability if everything's new, and your space can either sell faster or spend less time on leased, which can be a huge cost for a property owner. For a tenant or a property owner, again, depending on the lease type, seeing energy price stability really helps companies manage their bottom line. And you'll see that when you do a deep energy retrofit like this, a lot less fluctuation, especially when you do those measures like improving the envelope or improving anything that kind of reduces air conditioning energy use or reduces heating energy use. And then ongoing, if you've made this investment in equipment that's going to pay for itself in 5 to 10 years, you're going to see decreased operational and maintenance costs, as well as decreased capital investment costs when you make kind of these decisions by doing a holistic approach, smart and at the right time. And now that's the end of my presentation, so I'm going to open up the floor to any questions you may have. I think Josh is going to be able to do that.
Great. Thank you, Blake, and thank you, Betty. Wonderful presentation. We do have a number of questions that have come in. The first comes from Leanna. Would installing PV change the payback for space heating and water heating and make it more economical?
Yes, that would definitely be an opportunity to make it more economical. It really depends on what kind of utility program you have. That's essentially whether you have net energy metering, which allows, let's say in an office space which is closed on the weekends, you to send that energy back to the grid and be credited that on your future bills. In this area with community choice opening up, you're also seeing feed-in tariffs, which works in a different way, but kind of provides the same value. Battery storage, as those prices really drive down, would also be a real opportunity to increase energy efficiency here. This funding had to be really used to analyze energy efficiency as opposed to renewable energy. So that's why you didn't see PV in the model, but it's very rare that I'll not convince a client to add solar. So that's a really good point, Leanne. Thank you.
Thank you, Blake. Sort of a follow-up question from Robert. Regarding water heaters, does the payback scenario change if they are storing excess on-site solar energy?
Yes, that'll definitely change as long as you have a payback for your solar, which is true in most of the country. While we think of my home state of Pennsylvania in the Northeast as kind of less sunny days per year, which is true, when you compare that to kind of the leader (2000 to 2010 timeframe of Germany actually the United States. So it's and they've made it work. They have plenty of time, plenty of hours or days per year where only renewable energy powers Germany from really good investment and good policy. So as long as your solar pays back and you're making your own energy, there's certainly a case to kind of get off gas and still do it in a cost-effective way. Again, renewable wasn't part of this study, so we didn't look at it, but definitely the way to go. There's a particular piece of equipment I'm not sure if it's called the Sun Bandit or Solar Bandit, which don't want to plug them specifically, but it's kind of a hot water heater integrated with solar that's one specific system. Yes, it's called the Sun Bandit that you might want to look into, which is a solar integrated hybrid hot water heater.
Great, thank you, Blake. From Alice, her question is, do any of your calculations take into account the new proposed peak energy times? So we're talking 5 to 9 at night versus 2 to 6 in the evening.
I am greatly affected by the new peak times. I'm on an electric vehicle rate, so that's kind of already implemented for me. And since I'm on a level 1 charger, it's sort of killing me. I think I'm paying an average of 33 cents per kilowatt hour or something, which is obscene. It's almost triple the average. Our calculation to use the current rates, they didn't include the upcoming rate change. I'm trying to think through each of the energy efficiency measures, and just let me jump back really quick because it's a really good question.
Okay. Let me change presentation mode to back to you, Blake.
Sure.
Oh. You wanted to show a slide?
Yeah. I just wanted to pull the energy efficiency measures back to see what's going to really be affected by that 5 to 9. It's also based on building types. So let me scroll up to our building types. Offices are probably going to see a little bit of help from that shift in peak that we're seeing. And the peak that Alice is talking about is basically, for those that aren't aware, since we spent about 10 years driving people to decrease their energy usage from 12 to 5, actually more than 10 years. We spent 15 years doing that because the old peak energy usage was when air conditioning was on in the summer at high noon is when you use the most energy usage. Now that we have solar, which produces energy at the exact same time, we're seeing that peak shift to when everyone comes home. So it's really based on building type. You're going to see offices even start to get a little bit of benefit from that peak, especially on the electrification side. Retail, having LED lighting is going to be really important because that's when you're going to use a lot of energy, lighting energy from 5 to 10 or 5 to 9 when retail stores around me are open. Schools will probably benefit a little bit from the peak. Municipal, the fire station in this case, I would say that would kind of average out since it's running 24/7 and kind of gets the benefit of being open during that lower peak at night. The people that are going to get hit hardest, especially if they electrify, are multifamily. And I think what we're going to start seeing, I'm going to jump into a specific measure here. That's going to ding you on your heating side. Even though more heating energy is used after night. And hot waters, I think we're going to have to, if we go to electrification and we move this peak, we're going to have to see some smart hot water heaters that kind of allow the temperature of the water in the tank to float down a little bit during those peak hours in order to not get dinged with what might sometimes be 50 cents per kilowatt hour at those peak times. Really good question. I will admit that I'm a little worried about the peak shift hitting my own pocket. Thank you.
All right, thank you, Blake. This one's for anyone who's in the Northeast. Is it feasible to heat commercial buildings with heat pumps in colder climates, such as New England?
Yes, we've actually been doing a lot of studies with some colder climates. And again, I'm originally from a cold climate, so know that pretty well. There are plenty of areas in the Northeast. For instance, my in-laws heat with a heat pump. Their house was built in 1997, and the Toll brothers did not want to pay for the extension of gas to that neighborhood. So that entire neighborhood has been running at a heat pump for a long time. So there's an example. Commercial buildings are also completely possible. Any commercial buildings in that area don't have gas infrastructure. And then I want to point back to the example with Norway. Norway is using electricity to heat all their commercial buildings. So it's definitely something that's possible. What you will run into if you try to do a direct replacement from a gas system sometimes is a requirement to replace ductwork. It really depends. The issue there is that natural gas heating systems will often supply heating air above 110 up to 130 Fahrenheit, whereas you'll be supplying heat at 90 to 100 degree Fahrenheit out of a heat pump. So really good question. Norway's doing it, and they're really leaning on heat pumps to make that happen.
Thank you, Blake. This one's from Jim. You mentioned noise and comfort benefits of Empire State Building window replacement. Did you include the non-energy benefits of windows in your cost effectiveness calculation?
That's a great question and something that we need to be including more. It's brought up often, but we did not include the non-energy benefits of window replacements in this particular study. I know that in my particular case, I live in a beach community that's under the flight path of San Diego International Airport. We even have a whole thing called the OB pause, where in the middle of conversations you have to pause to let the plane go by, or pause your movie to let the plane go over. So noise is a really big issue for us. I would say in my case, I would pay about an extra $100 a month to have dual pane glass. And that's something that maybe for multifamily, since I live in multifamily, we could include. So I might run some calcs on that and do some kind of anecdotal questions to some of my friends who are running into the same issues. It really depends on if you have real noise issues, which you're definitely going to see in urban areas, or if you're like me, living near airplanes.
Thank you. And I think you might, if you're able to, go to the avocado tree slide for this question. Jan Grigier asks, she states and then asks, the avocado tree example would be more compelling if the cost of picking an entire tree was less than the sum of top to bottom individually, which is the case due to setup time at least. So basically, is there a do everything at once savings with energy efficiency?
Yes, there definitely is, in that you'll have less downtime at your facility. But then the other kind of point here is that what you see happen a lot with ESCOs, and I've seen this in the university and federal level, especially from 2005 to 2015, which is I was mostly pushing, is that an energy service company works a lot like a power purchase agreement, if you're familiar with that, where the energy services company will come in and replace some of your equipment for free up front, and then the energy savings that you'll have, instead of paying that to the utility company, that energy savings is paid to the energy services company to pay off the equipment. Once that's paid off, the energy services company has made a little bit of money. From then on, you start saving money, and carbon's been saved by everyone. The issue there is what we've seen is when they come through, they're definitely going to do lights. Let's see if I can get my pen to work here. Lights, pumps, and motors. That's their bread and butter. If they come through and do that, and you do that first, you're going to miss the ability to kind of share the energy savings and pay for some of those measures that you really want, like windows, which have just too long a payback to make sense to change on their own. And that's what I was kind of pushing there. But the setup time, including less downtime, is really important. I know that when our office building had a flood about a year ago, we were down for a couple of months, which was a big issue to disrupting our business. And that's something that probably the building owner should have done a few upgrades while he was in there to make sure to not so much downtime for his tenants. We ended up not paying for those months. Really good point. Thank you.
Thank you. Another question from Ezer. Do your costs and benefits calculations consider the impacts for customers who are not electrifying? For example, if 90% of the community electrifies, what cost benefit impact is there for the 10% of the community who does not?
It sounds like what you're getting at is the additional cost that we're going to see for if 90% electrifies and they disconnect their gas meter, then the 10% are going to have to pay for the maintenance costs of the gas infrastructure across the whole area. That's a really good question, and I think an economic issue that a lot of cities and states are running into as they look to electrification. I know that the state of Connecticut was looking at basically, as you might have seen from last night's State of the Union, all our infrastructure that we started building during the days of the New Deal, some of that includes natural gas infrastructure, basically has a 40 to 60 year shelf life, and we're there now. And we made a lot of decisions in the 80s and 90s and 2000s to not replace that infrastructure ahead of time. So we're seeing a lot of failures around me. I'm getting a ton of water main breaks. So we are going to see a lot of replacement of the natural gas infrastructure over the coming years. I would not like to see 10% of the ratepayers have to pay for that replacement. That would be a problem. What we might have to look at when a big natural gas replacement project comes through like that, and I know that Connecticut looked at this exactly, is how much does replacing all that gas infrastructure cost? And is it cheaper to just replace everybody's HVAC systems with heat pumps? That's something we really have to balance as a society, and starts to become very nuanced when you get to different business entities playing in the game. So I don't necessarily jump into who should make money there or how that should work. Obviously, gas companies are going to want gas infrastructure replaced and ratepayers to pay for it. Companies who only sell electricity or want more electricity usage. So it gets very nuanced. It's something that really has to be looked at state level, and in terms of what's going to be the least cost society-wide and for their constituents is my take.
Great, thank you, Blake, and thank you, Betty. That's about all the time we have for questions. And if everyone can see my screen now, we've got the contact information for both Blake and Betty, so don't hesitate to send them an email regarding any additional questions that you have, or any information on our initiatives with our work with DNVGL. And with that, I would like to quickly point out that on our website, which is where I am right now on my computer, if you go to Our Work, and under Our Work, Peninsula Advanced Energy Community, also known as the PAEC initiative, if you go onto that page, we do have the energy efficiency and fuel switching reports for commercial scale buildings accessible there. If you scroll down just about a quarter of the way. These will also be sent out in a link with the webinar recording and the slides that you were shown today on the presentation within the next 2 days, definitely by the end of the week. So once again, thank you very much, Blake and Betty, and everyone for attending, and we'll talk to you all soon.
Thank you so much.
Thank you.